the amazing radio and superluminary observations we already had. If not, I might take the time to share the screen. And this is what I was talking about, NGC 2371. So this is a paper published by our group last year. So this is an image combining Canada, France, Hawaii telescope observations and HST. So you see these bow shocks around these low ionization structures. This is like photo, but we believe this photoablative flow similar to what we see in Orion proplyds. So my impression is that the maximum of the radio emission is just coincident with this. This is the hotter region, closer to the star than within the dense and cold material. Do we have comments, or does anybody wants to say something? Maybe as Ursula said, maybe somebody wants to express their desires for future ALMA observations, for example, which are proving to be every time more and more amazing every time we observe any object with ALMA.
Yeah, if nobody raised a point, maybe Carmen can go back to the object she described, OH231. What do we know about the lots of information? It will be nice to kind of see what we understand there. So, for example, what do we know about the binary?
You mean the question is for Carmen, for the
Carmen, yes.
Yes.
Yeah.
Yes. We don't know much about the binary. I mean, we don't see the stars directly, right? We only know the spectral type. I mean, we only know there is an 8-0 main sequence star with the AGB QX book. And the only information we have about the orbit is what I presented today, because it's the only, I think it's the first time that we see something that could tell us, we see the position of the central star relative to the disk, to that disk, which is rotating, then it's circumbinary, or probably circumbinary. Then this is the only way that we have been able to guess, more or less, what is the separation with this companion.
So you know this only from the angular momentum of the disk, that you need to supply the angular momentum.
The angular momentum of the disk, Ursula asked about that. I computed that, and it is, I computed the angular momentum of the surface layers of the disk that are emitting in sodium chloride, and this is equivalent to the angular momentum of a 10 Jupiter mass planet orbiting around 1 AU. I don't know if this tells you something, but I mean, it is of course much larger than the angular momentum that the progenitor star will have. I mean, can supply.
Okay.
But it's a small fraction of the binary of the angular momentum stored in the binary orbit. If we believe that there is a 2 solar mass companion orbiting around 23 AUs.
But it's far, right? The companion is really far. Did you say 23 AU?
Mm-hmm.
Is that projected, or what?
No, this is deprojected already.
Deprojected.
Yeah, but it could be an eccentric orbit, Ursula. So the fact is 23 AU doesn't tell you that it doesn't get closer.
Yes. But I mean, like, for example, if you do the numbers, this is what I was presenting in one of the last slides. It is far away, but it's very massive. And this object, if you take into account all the parameters, meets the conditions for mass transfer under the Windrow's low overflow mode.
I mean, we already know from the Myra binary, which is projected separation, which is even larger, that interaction is taking place between the two stars. So I don't think that 23 AU is a big impediment
It's not too
to,
much. Yeah, I
yeah.
think it's not too large. Yeah.
I don't know. I'm gonna chant the usual song that this. So we had a paper a while ago where we tried to figure out whether NOEM's required. So NOEM had proposed something where you have a periastral passage with some ejection at that time. Remember, and you can do the game of matching the energies of in the ejecta with the potential accretion and excretion from a jet and etc. etc. And we came up with the only solution was to have a merger that would be basically, again, would be a common envelope merger, which would leave the AGB star intact, right? Because if you don't have a merger, then you reduce the AGB star to a post AGB star, which we don't want to do. And then the outer companion, the one at 25 AU, it's a bystander having played only a dynamical role in the life of the trinary or the triple over longer time scales.
Yeah, this doesn't go against to what we see now. I mean, what you're suggesting is I guess what I also said in the end, that something different may have happened 800 years ago that resulted in the ejection and the shaping of the large-scale nebula, where there is indeed evidence for fast ejections, right? And those are the lobes that actually have the large linear momentum and everything, the ones that you cannot explain with radiation pressure. But what is going on now at the center is just maybe a kind of a smooth shaping of a bipolar thing, maybe just due to the fact that the survival, in your scenario, right? The survival binary is also there, and then is interacting with the Myra, and then it's forming this dense structure, and just the stellar winds is just coming out through the pores, which are the low density regions. I mean, it's not incompatible, I think, with what you propose.
And we try to match all the numbers. It's a little bit tight, and you pull and push to just make sure that you got the numbers and the masses, but it's not crazy. Can I ask, do you have an opinion on this?
Before we go on to the next thing, can I just add that in the case of Myra, even though the companion is very distant, you see a connecting material between them in the X-ray images. So there's clearly interaction going on between the distant companion and the primary. And so it's observationally, we know it's possible.
Yes, but it's
You guys have to figure out why, what it's
not at the origin of the main ejecta, maybe something going on today. But can I ask about, so do you have, Carmen, an opinion about the lopsidedness of OH231? I mean, that is really challenging.
The different sizes of the north and the south lobes.
Show
No, but
your slides. Show your
now-
slides. Not everybody here familiar with this lobe.
Well,
you
you've got a
want
tiny lobe and a big lobe.
Okay. Do you want me to share my screen?
Yes, yes, why not?
Just
Okay, and now let me go back to the
You
beginning.
see that also you mean the unequal two lobes?
yeah, the usual bizarreness of this object is this asymmetry.
Yes.
Let me go back. This goes very slowly.
It might be related to the displacement of the star from the center of this.
Yeah, there are so many things that we don't understand about this guy, that the difference between the size of the north and the south lobe is not the thing that worries me the most now.
Like, okay, here you
But-
have it on the left.
Yes, for example. Yeah.
Isn't that, it worries me the most, is good. It's just a punch in the face. It's
Yes.
so,
Well, yeah, I don't know. I think in for example, in Guillermo's García Segura models, or I don't know if it was in his models or in some of the models by Adam, I think it was under the common evolution scenario, right? I think they could kind of explain not unequal polar ejections.
so Valentina has something to say, but just let me say one thing to that. Yes, so in Adam's models, the reason for asymmetry in the jets was, first of all, there was a relatively low momentum of the fast wind, which is, and then the environment created by the common envelope is extremely 3D, right? That means it's got some symmetries, but it's got a lot of asymmetries, and that created the asymmetry in the jet. So I feel that a 3D environment, meaning where the symmetry is somewhat broken, can give you something like this. But you know, I still don't know. Valentin.
I would like to comment on the different size of the two beams, of the two lobes. If you measure also the mass of each of these components, it happens that another one, which is the smallest, is denser. And when you calculate the momentum, in fact, both momenta are quite similar. So one has the impression that the north lobe, which is the small one, is just flowing more slowly because its mass is higher. That's from the observational point of view.
Valentin, do you mean that I would say that the underlying jet, which is creating that cavity, which you see in the lobes, the underlying jet has different momenta in the north and the south?
No, what I mean is that the momentum transferred to the lobes is the same, but the mass of the northern one is higher, so the velocity must be smaller. And if the velocity is smaller, which is also confirmed by observations, if the velocity is smaller, in the same time you don't get so far as in the south lobe.
Correct. Okay. So the velocities are different on different sides. We know that.
Yes, they are different, and they are proportional to the size of the lobe.
Okay.
So it could be just a problem of different mass. And also, if you look at the mass of the small, the rotating torus detected in sodium chloride, it happens that the northern one is also denser and more massive. Do you have that image, Carmen?
I was looking for the table with the momentum. I mean, I think you're right. Basically, there's a small difference between the momentum between the two lobes, but it's very, very small. I mean, the north actually has a little bit more momentum than the south. But yeah, I don't know if that is within uncertainties, right? Let's say maybe
It's probably not significant, but
exactly.
I think is to be accounted for.
Mm-hmm. So you were asking about something else. What was it? You said that I should show something.
No, that was my comment.
Okay.
Ursula, I have a question for you, if you don't mind my asking you, and going back to Myra again. Ursula, are you there?
Yeah. I'm here.
Yeah, so when I was talking about the interacting bits in binary, you said, well, that is something recent going on, and that could not have produced the binarity and the jet-like outflowing this. Why are you so confident about that?
I don't know. It's like the main ejection as 800-year kinematic age. There's a lot of mass in there. It looked like some event, right? I'm not saying.
You're talking about Myra.
Again?
We're talking about Myra, not OH231.8.
What did you say, Raghavan? Okay, no, that's not the case. No, that's God knows how long that has been going on for.
I said, are we talking about the same object? I'm referring to Myra.
I understand.
Okay.
No, so that doesn't have. No, I have no comments on Myra.
Okay, I was talking about Myra. So I was saying that Myra has a distant companion, 75 AU in projection, and yet you can see the interaction
Yes.
between them in the images. And so I'm wondering, are you saying that theoretically it's impossible that companion could be responsible for the bipolar ejections that we see in this object?
No, but isn't Myra has you know, there's the bridge and so on, but it looks to me like it's something that's happened over a very long time scale.
No, I'm not
much
talking about that
longer.
long thing. There, if you look at the central region, there are bipolar ejections, fast bipolar ejections in that from
On
Myra.
Myra?
Yes.
And the central region, you mean the companion or the Myra?
Well, we don't know where, of course, we can't say where the ejections are coming from. We don't have that kind of resolution. But I'm saying that system, you have a distant companion. You can see a bridge of material connecting the distant companion with the primary, and you have bipolar ejections. So why couldn't it be possible that this distant companion in an eccentric orbit causes these bipolar ejections?
Because where's the energy? I mean, this with OH231, we have so much momentum and so much energy. You need an engine, you need something to provide it. And you know, the classic we go back to is some kind of gravitational engine. So you have an in-spiral or a merger, you know, you need to pump some serious energy into that object that does something 800 years ago that was confined in time. It was an event.
Coming back to OH231.8, I'm talking about Myra. So the total amounts of mass and other ejections are different there.
Yeah, but so I don't know anything.
The point I'm trying to make is that things which you see, which look like distant, or the binary separation looks large, they may be eccentric. They may have large eccentricities. I mean, V Hydra is a very nice case where we can clearly see that every 8.5 years or so, it goes very close to the AGB star, produces these high velocity bullet-like ejections, and then, you know, and it happens every 8.5 years. So we have to consider taking seriously into account eccentric binaries.
Yes, but can I ask you about this one of the, I think we talked about it in the past, but what we notice is if you have mass transfer at periastron passage, you have a change of the orbital parameters that will be in proportion to how much mass transfer you have. And so to maintain a very, an orbit that is eccentric and is transferring mass at periastron stable is really difficult.
Right, so there's a solution.
If you have 8 years, you're going to really collapse that orbit.
I have an answer for that. So in the case of V Hydra, there's a paper by Mark Morris and collaborators with a tertiary, there's a tertiary distant thing that is maintaining this eccentricity. So we have to seriously start thinking about triple objects now.
But if you have mass transfer or mass loss of periastron, mainly changes the upastron, not the periastron. So it's not a big deal. It's if it causes mass loss, the orbit will increase, but not the periastron, the upastron, if the mass loss is around periastron. So we can have periastron.
You're just doing the.
Excuse me?
But you're just doing the orbital change by mass transfer. So you change the relative masses and then you look at the new orbit. But what about if there's drag? You know, there's
tidal and so on, but there are several effects. There is a tidal mass loss from the more massive one will increase the orbital separation, and mass transfer from the massive to the lower mass star will decrease it. But the main effect will be on the upastron, on the furthest point. So, but the orbit can stay stable. You know, Amit Kashi performs.
Can it remain eccentric? Can it maintain its eccentricity?
Oh, definitely. You can increase it or decrease it. Depends where you lose the mass and where you transfer the mass in the orbit. In Eta Carina, the great eruption, we did simulation of massive stars, but of total 250. But still, the system lost 40 solar masses. I mean, say 15% of the mass, or even 20. But still maintain eccentricity on the orbit, because if you transfer some mass and lose other, the orbit changes, but can stay there. So this can stay for a long time.
So this discussion is very interesting. So I would love to hear some of the younger people, if they have any opinion, if they have a wish list, as Ursula suggested. Maybe they can think of it for tomorrow. If not, I want to also point out a very interesting discussion on the molecular emission and the COH, which was this HCO plus molecule. So maybe Joel wants to comment about this.
Yeah, well, I think we already discussed it briefly, this kind of chicken and egg problem. Do shocks generate HCO plus, or do the X-rays produced by shocks drive the HCO plus production? And I think, you know, it's not an easy thing to disentangle, bottom line.
So in particular, you mentioned that this can be ionized by cosmic rays in molecular clouds, but is this the case also for protoplanetary nebulae or planetary nebulae?
Probably not, no. I think that the only real ionization source you have in molecular clouds, well, okay, molecular clouds that don't have lots and lots of young stars forming in them yet, say, is cosmic rays. If you've got a lot of young stars hanging around, then you've got a lot of X-rays, and so that can contribute to HCO plus production. You just need something that'll ionize the molecular hydrogen to initiate the reactions that end up with HCO plus, I think is the bottom line. And I'm not, you know, I'm less well-versed on the shock mechanism, so maybe somebody else can talk about that. I assume it's just, you know, you need whatever energy is necessary to send the same sorts of reactions going. I mean, what is the process? I don't even know.
We have Valentina, I saw a hand, or Javier, I'll go there.
No, the process in the case of shocks is as long as your shock is ionizing the environment, then you have the ions, and then you form H3 plus. And once you have H3 plus, then you can transform CO in HCO plus. That's the typical formation pathway. Yeah. And you can ionize the gas via shocks, or because you have UV, or because you have X-rays, or because you have cosmic rays. It depends on your source. I mean, if your source is cool enough, then maybe the answer is shocks. If your source is powerful in X-rays, maybe you are tracing the XDR. If it's strong in UV, then you have a PDR, standard PDR. It all depends on the conditions. As long as you form the H3 plus, then you will form HCO plus out of CO.
Yeah, but as Joel suggested, said that also shocks produce X-ray radiation. So,
but in that case, you really need to have very, very strong shocks. But of course, you can also do it. I mean, for example, I'm trying to recall, but I think that the jet you see, for example, in Area Query, you see this jet shining from long wavelengths in the radio up to the X-rays. I mean, whatever. It depends on the shocks you have and the environment and how hot you get after the shock.
Yeah. So. Perhaps what we need are unfortunately, or fortunately, some really good models that can reproduce some of the conditions. For example, in NGC 7027, where we think we know the mechanical speeds and so on. We may not know the shock speed so well, but we know the velocities pretty well. So perhaps we can figure it out somehow.
In the case of NGC 7027, that's probably the X-rays of the UV. I mean, as we have already said in the paper, I mean, the shocks are not going to produce any of those. It must be direct radiation from the central star. That's another. But for example, in the case of OH231, you are not expecting to have any source emitting X-rays or even UV, and probably in this Lucero sources, they don't. I mean, you are not expecting any central source emitting in the UV or in X-rays. Then shock is an option. Yeah, but not shocks producing X-rays or whatever. Just shocks ionizing the material. Once you start ionizing the material, the reaction from CO into HCO plus is very fast and very efficient.
Sorry, in the Lucero objects, these are young planetary nebulae, so you have UV from the central star. Are you saying that's not enough?
Well, you have UV, then you have to do the numbers.
Yeah,
And you
but you can't rule it
really need
out.
to do the numbers and see if whether this UV flux is able to ionize in the degree of ionization you need to explain the H2O plus emission.
Well, it's obviously ionizing gas because you're looking at planetary nebulae, so you have ionized gas.
That's right. Yeah. Then
And you need a combination of everything. So young planetary nebulae, which will be dense in order to shield outside the molecular emission, but the stars should be hot enough in order to produce ionization and wind that will produce. So you need all of this as a recipe for disaster.
Yeah, I think it's interesting actually thinking about this a little bit further. It's not just enough to get UV. Correct me if I'm wrong, but I don't think you just need UV. You need soft X-rays really to start ionizing enough molecular hydrogen to generate HCl plus. You know, so that is maybe a tipping point, is to understand how much soft X-ray flux there is.
Wait a moment. Why do you think that the UV is not enough to ionize the hydrogen?
Molecular hydrogen, well, you need a fair volume of gas ionized, right? And I think X-rays are pretty good at doing that because they penetrate quite deeply. I think the ultraviolet's going to give you a photodissociation region as opposed to it's going to be a sort of a surface effect, and so you won't get much of a column of HCl plus. I'm just talking off the top of my head here, and we're down in the weeds, so I don't know. Probably
Valentin.
calculation.
Sorry. Yes, my comment is that it's not enough to have a lot of UV to destroy molecules, because in fact, it also depends on the extinction to the molecular layer. For instance, in NGC 6302 that we have seen yesterday in a couple of talks, there is a lot of UV emission. The star is very hot, very, very hot, and however, we do detect molecules. And the reason is simply that the dust torus is very, very dense and opaque. So molecules can be shielded by this, by not only by dust, but also self-shielded. So finally, it's not enough to say we have UV, so we don't have molecules. We don't have molecules where they are exposed to the stellar emission. Otherwise, they can be very abundant. That is the case of 6302, but also 7027 and many other sources.
Yeah, that's what I said. Very young planetary nebula, that they will still be dense and probably shielding the outer material.
Exactly.
And at the same time, hosting a hot bubble, for example.
Well, in the same planetary nebula, you have both regions, right? You have the shielded regions, which are generally the tori, right? Where you see the molecules, and then you have the bubbles, which are not that well shielded and where you see ionized gas. So you have both kinds of material present, molecular material as well as ionized material.
And also you may have a PDR, because
yes,
systematically between
sure.
between the H2 region and the CO-rich region, there is a PDR. That is the example of 6302, in which the PDR is probably the dominant component from the point of view of the mass, total mass. And it's also the case of the red rectangle that we have seen. There is a kind of a small H2 region in the middle, a lot of molecules far from the center, and there is also a PDR where the material is directly illuminated by the stars, the central stars.
Yeah, we showed in the Ring Nebula with SOFIA observations that the atomic component was the dominant mass component. Neither the ionized gas nor the molecular component compared to the amount of mass in the atomic PDR. Yeah.
I'd encourage everyone to have a look at, again, at Jesse Bublitz's poster on NGC 7027, where you see the enormous difference in morphology between the molecular hydrogen and CO plus emitting regions versus the HCO plus region, which is larger and sort of is where you expect if the X-rays are penetrating more deeply than the UV, just as Valentin pointed out.
Okay, if we do not have any further comments, I would love to finish the session by clapping and thanking all of the speakers. Please unmute yourself and then we can. Martin, do you have any announcement?
No, nothing to say. So we will meet again tomorrow, last day, but still we are strong enough for more discussions and thoughts. Thank you very much.
What time
everybody.
are we meeting tomorrow?
Tomorrow is 10 GMT,
Same as today.
same as today. Yes.
Okay.
Okay.
Thank
See
you,
all
everyone.
there, guys. Thank you very
everyone.
much.
Bye-bye.
Bye.
Bye.